Hi, I'm Vered, and I'll be talking about a long, hard look at multi-word expressions in the age of language models. The main research question I'll be investigating in this talk is the extent to which text representations address multi-word expressions. In the previous decade, we had word representations, whether sparse vectors or word embeddings, and it was common to represent multi-word expressions by learning a function that composes the constituent words. Sometimes it was trained to approximate the distributional vector of common phrases. And these models were typically constrained by a fixed phrase length, typically 2, and were often developed for only a specific type of phrase, such as adjective noun composition, for example. Then came along RNNs and enabled learning a function for variable length phrase. And these models sometimes were trained on some downstream tasks, and then the phrase representations would be a byproduct of the training. Then in the last 3 years, pre-trained language models or contextualized representations completely changed the landscape of NLP. And something that's interesting about these models is that they are trained to represent each word in a sequence as the function of all the other words in the context. So in a way, we get phrase representations for free, but how good are they? The main limitation of representing multi-word expressions in a compositional approach is that sometimes the whole is greater than the sum of its parts. In particular, two problems that emerge are first, that when words are composed, that they often create implicit meaning, which is not inherently a part of each one of the constituent words. For example, baby oil is oil used for babies, which is different from interpretations of many other compounds that have oil as a head. The second problem is that non-compositional phrases involve detecting and handling meaning shift. For example, monkey business is not related to monkeys. In this talk, I will discuss the capability of current representations to interpret implicit meaning in multi-word expressions. And then we'll talk about the ability to recognize when words are used non-literally and the interpretation of such figurative language. Let's start with interpreting implicit meaning. Some examples of phrases that involve implicit meaning are noun compounds, as in the example of olive oil, which is oil made of olives, versus baby oil, which is oil used for babies, and adjective noun compositions. So for example, heated water refers to the temperature of water, but heated debate refers to anger or passion. Do text representations capture implicit meaning? 2 years ago, we had a tackle paper in which we probed existing text representations on how well they capture implicit meaning and meaning shift in various types of multi-word expressions. Specifically for noun compounds, we had the noun compound paraphrasing task in which we had a sentence, like a sentence including a compound, like a township. The township is served by 3 access roads. And then we had a candidate paraphrase, such as road that makes access possible. And the goal was to determine whether the paraphrase may describe this noun compound or not. We used various different representations, specifically 3 static word embeddings, word2vec, glove, and fast text, and 3 contextualized representations, the only ones that existed back then, I believe, which were Elmo, GPT, and BERT. And then we kept the representation frozen because we were interested in what ability they already have from their pre-training. So we embedded the sentences, we possibly also encoded them with an additional encoding layer, which was either BIOSTM, self-attention, or no additional encoding. Then we pulled the representation to get a single vector to represent the noun compound and the a single vector for each of the noun compound and the paraphrase, and fed it into a classifier to predict true or false. We found that while language models were better than static embeddings, they were still far from humans and much closer to the majority baseline. And then because it's been 2 years since then, and there are many new models, then I repeated the experiment with a newer model. Specifically, I used GPT-3. And this was different because it was in a few-shot learning setup, so I provided it with 100 training examples. And then that was slightly better than the previous results, but still very far from humans. Then we had a similar task with the adjective noun composition. So given a sentence like to-go cocktails triggered heated debate during legislative hearing. We also had the attribute of temperature, which would be similar to the paraphrase in the previous task. We embedded each one of them, and then we predicted whether the attribute may describe the adjective in the context or not. And here the results were still far from humans, although BERT performed substantially better than the static embeddings. And again, I repeated the GPT-3 experiment, and here it actually performed slightly worse. Not slightly, it performed worse. But it kind of works in practice, right? When you use downstream applications like translation, it kind of works, at least for the common phrases. So here's an example of translating olive oil and baby oil to Italian. And because of the properties of Italian, it would be translated with a preposition, and then it's less ambiguous about whether it's translated correctly or not. And this is a good example. But that's not always the case, especially when you work with less common phrases. Here's an example. Translating grass-fed yogurt to Hebrew would translate to the equivalent of yogurt with grass, which is incorrect and also disgusting. And what happens here is that there's some implicit meaning that is not conveyed and has to be translated explicitly to Hebrew, because we don't have I don't think we have any implicit expression to mean grass-fed yogurt. So can we train models to handle such uncommon phrases? The motivation for that would be that people actually pretty easily interpret meaning in concepts that they've never encountered before, based on our existing knowledge about similar things in the world. So for example, if you asked me whether I'd like a parsley cake, I can reason about what it is, because I know that cakes can be made from fruit. Parsley is an herb, and herbs are similar to fruit. Then it's probably cake made of parsley based on that, and then politely decline. And we can simulate this human reasoning process by looking at corpus occurrences. So for example, the template cake with something appears with foods such as chocolate, lemons, strawberries, etc. So parsley sort of fits into this distribution. So this was the motivation for our ACL 2018 paper, in which we worked on non-compound paraphrasing. And we actually worked on the original and generative version of the classification task we discussed earlier. Given a noun compound, the goal is to produce a ranked list of paraphrases expressing the relationship between the constituent nouns. So for example, olive oil is oil made of olives, oil from olives, oil extracted from olive, etc. The model we developed gets as input the noun compound and outputs a list of paraphrases. Each instance in the training data is composed of W1, such as olive, W2, such as oil, and a single paraphrase, such as W2 made of W1. Our main task is to predict the relationship, to predict a paraphrase given the noun compound, which is like answering the question, what is the relationship between olive and oil? And to answer this question, we use word embeddings, and we create this missing paraphrase, oil placeholder P olive, for which we have these special placeholder embeddings. And we encode the sequence with a BILSTM and take the output vector corresponding to the placeholder and feed it into an MLP that predicts paraphrase from our predefined vocabulary. So we basically reduce the task to a classification task. And then we can compute cross-entropy loss between the predicted paraphrase and the gold standard paraphrase. We train this in a multitask setup, so we also have two auxiliary tasks in which we predict the nouns. So that would be answering the questions, what can oil be made of, and what can be made of olive. And then these tasks are trained with the shared parameters and the losses are summed. So the main task embeds the similar noun compounds such as avocado oil in proximity to olive oil due to the similarity between the constituent nouns. So oil and oil would be identical and avocado and olive are somewhat similar. And then as a result, when the model sees a new noun compound, it can predict the same paraphrases based on similarity to observed noun compounds. The auxiliary task embeds similar paraphrases in proximity based on the nouns that they occurred with. So for example, a paraphrase like W2 from W1, although it is lexically distinct from W2 made of W1, it would be embedded in proximity. And all these tasks are supervised by paraphrases extracted automatically from Google Ngrams. During inference, we predict the top K paraphrases for each noun compound, and then we have a re-ranking component, which I won't get into. We evaluated the model on the SemEval 2013 task 4, and the task has two designated evaluation metrics. Here I only focus on one of them, which would be the isomorphic matching score. The other one, the non-isomorphic score, is less strict and it typically favors the majority baseline, so it is less informative. The isomorphic matching score goes from 0 to 100 and it rewards recall, precision, and the order of paraphrases predicted by the model compared to the paraphrases suggested by human judges. Our model achieved the best performance thanks to a good recall precision trade-off. And we also conducted an error analysis. So first, looking at false positives, these are paraphrases predicted by the model that were not included in the references. So a large portion of them are actually valid, just not included in the references, as typically happens with generative models. Then we had 15% that were too specific, for example, predicting life of women in community instead of life in community for the compound community life. And some other types of errors, for example, there were some paraphrases that were generally correct, but just sound borderline ungrammatical, like force of coalition forces. Among the false negatives, we missed a lot of paraphrases that were too long for our model or that contained determiners and inflections, which we removed. And again, because this is from 3 years ago and it is ancient history in terms of modern NLP, I ran some additional experiments using newer models. So first, I trained encoder-decoder models. So now it's a completely generative model. I used BART and T5, and I trained them to predict a paraphrase given a noun compound. And I did the same with GPT-2, which is trained in a slightly different manner as a language model rather than an encoder-decoder. And also GPT-3 in a few-shot learning setup with 100 examples. And then for each of these models, I sampled 5 predictions with beam search for all models except for GPT-3. The API forces you to use top P prediction. So you can see that based on the scores, it seems that these models are somewhat worse than our multitask learning model. But to be completely fair, our model outputted a much larger number of paraphrases, and we also had a re-ranking component. So it's not a completely fair comparison. And in addition, if you actually look at the predictions by these models, they're actually quite good. So I think here the problem is the scoring function, which is not the most informative, which happens a lot with generative tasks. That you don't really have a good automatic metric for it. So let's look at a few examples by these new models. So this is an example noun compound from the test set, bus conductor. And most of the outputs are valid. I marked the ones that are invalid with in orange. So some of the predictions are actually quite generic, like conductor of a bus. If a model doesn't know anything, it's going to be very useful to just predict W2 of W1. That's often valid paraphrase. But some of them are actually quite specific, like conductor who works in a bus or conductor who drives a bus. Here's my go-to rare noun compound, parsley cake. And here I was really impressed because the predictions were perfect. I couldn't find anything wrong. And I think what happens here is that what my model was doing explicitly, these models probably do behind the scenes or because of their pre-training, they just generalize from existing knowledge about similar compounds. Finally, this is an example borrowed from a talk by Yajin Choi a few years ago, cheeseburger stabbing. And here, most if not all of the outputs are invalid, especially GPT-3, which really nicely tries to predict any possible interpretation. And I guess the common problem here for all models is that they struggle with noun compounds that require common sense knowledge to interpret. For example, here you need to know that you can't stab someone with a cheeseburger because it's soft and you have to use a sharp object to stab someone, or that someone stabbed a cheeseburger is not something that is newsworthy and it's not going to be mentioned in text. I'd also like to point out that in all my experiments, I treated the interpretation of noun compounds as independent of their context. But this is not always the case, and we are capable of interpreting noun compounds differently in different contexts. For example, if you see cat milk on the supermarket shelf, you're more likely to assume that it is milk for cats than that it is milk from cats, although I honestly don't understand why this product exists. Yeah, some people actually do need this clarification. And one last comment on this part of the talk is that while my model and the newer models perform pretty well and generalize to unseen noun compounds, what they don't do by design is to interpret non-compositional compounds. For example, if you want to understand the meaning of crocodile tears in this context, given a headline such as "Furious Meghan Markle says she won't fall for dad's crocodile tears after he claimed she'd be better off if he were dead." Here, it's going to be very hard to interpret it based on the context because it requires understanding of the narrative, getting to know the characters, making some common sense inferences that to understand what is implied by this context, etc. And this is pretty complicated. And so first question we can ask here is whether representations actually know that this is not about a crocodile. And this leads me to the next topic, which is recognizing meaning shift, which is when a word is used differently from its common literal meaning. In our tackle paper that I've discussed earlier, we also tested this. So for example, we had a task of noun compound literality in which we had a noun compound in a sentence, and the model needed to determine whether the constituent, one of the constituents of the noun compound, is used literally or not. So for example, in the sentence, "The crash course in litigation made me a better lawyer," the word crash is used not literally. And so we probed the same representations for this capability. And the answer in the case of contextualized representations was absolutely yes. They're very good at it. You can see that they are at human level. We also showed the same for verb particle constructions, such as get on, and light verb constructions, such as make a decision. And contextualized representations were just very, very good at this. And it's actually quite reasonable because if you think about it, they are very good at word sense disambiguation. And here they just recognize that the common sense, the sense of the target word in this context is different from its common and literal sense. But the question is whether, apart from recognizing that a word is used non-literally, do the models actually model the non-literal meaning in a meaningful way or not? So one way to test it was by looking at the substitutes of the target word in a sentence. So by basically masking out the word and then querying the language models for substitutes. And in this, here's a literal example, literal usage of the word trip. So the queen and her husband were on a train trip from Sydney to Orange. And here the language model suggests pretty good substitutes like ride, carriage, journey, traveling, etc. So that's good. But when we test the non-literal meaning of the word trip, so here, for example, we have creating a guilt trip in another person may be considered to be psychological manipulation. And here the predictions are much worse. So based on not just this single example, but multiple examples, we hypothesize that models are not as good at interpreting non-compositional noun compounds as they are at recognizing the non-literal word usage. And here's a new example from GPT-3, I used it here in the chat setup. So it suggested opening with, hello, how are you? Which I did. And then GPT-3 replied with, I'm an AI created by OpenAI. How can I help you today? And so I asked it the very important question, are there fleas in the flea market? And GPT-3 replied, if you're referring to the flea market, then yes, there are bound to be some fleas. So yeah, this is not perfect. So finally, this leads me to the last part of the talk in which I will discuss recent work that I've done with Tuhin Chakrabarty, which was an intern at AI2. And in this work, we wanted to quantify the ability of representations to model the meaning of idioms. So we started by creating a data set, and we used existing idiom data sets to compile a list of idioms. And then we found 5-sentence paragraphs in the Toronto book corpus containing these idioms. So for example, here's an example narrative. Everyone smiles. You should probably tell your parents about the wedding tomorrow, Carmen suggests. What about you, I ask, not thinking that she will be okay. I'll be fine. Since Dominic isn't up for grabs anymore, I figure that I will concentrate on something else, Carmen declares. So here we have the idiom up for grabs, which means available or obtainable. So we asked crowdsourcing workers to suggest one plausible and one implausible continuation for this narrative that depends on interpreting the meaning of the idiom correctly. So for example, they suggested as a plausible continuation that Carmen will find someone new to be with, and an implausible one, Carmen will continue to pursue Dominic since he is available. Then we train multiple types of models to predict the correct continuation. We define 2 tasks. One of them is the discriminative task, in which the goal is to predict which of the 2 possible continuations is the plausible one. The first type of models we evaluated were zero-shot models. So basically just using pre-trained language models and computing the language model score of the narrative followed by each one of the continuations and predicting the more plausible continuation, or the one that has the better language model score. For this type of model, we used GPT-2 and GPT-3, and we also used a T5 model trained on unified QA. So unified QA is a unification of many QA data sets. So what it provides here for the model is first some familiarity with the QA format, and in addition, also some of the, at least one of the QA data sets in unified QA is based on narratives, so sort of like similar domain. And indeed, unified QA performed substantially better than the other two models, thanks to its relevant training. But all the models were still pretty far from human performance. Human performance here was based on native English speakers who were provided the narrative, but were not provided the definition of the idiom, although I don't know that they didn't Google it, but that's fine. And as you can see, it was pretty good. The second type of model was a few-shot models, so we used GPT-3 and prompted it with a few training examples, each training example containing the narrative, the possible continuations, and the correct answer, which one of them is the plausible one. And then we predict the outputs for the test examples. We also use the PET model, which is similar, but uses a different model. It's based on the Albert model. The PET model reformulates the examples in a closed style, as a closed style sentence. So we got a small improvement over the zero-shot models with PET, but GPT-3 actually performed worse. This is actually due to technical limitations. That's because the GPT-3 API limits the number of tokens you can input, and because our examples are pretty long, we could only input 6 training examples, or 6, it's not exactly training, prompting examples, as opposed to PET that was provided 100 examples. We also had a standard supervised model in which we just fine-tuned Roberta as a multiple choice task. And it performed much closer to humans. Finally, we had 2 knowledge-enhanced models, and they were inspired by a paper by Cooper in 1999, which is a paper from language education in which he experimented with providing idioms to L2 English speakers and then when they don't know the idioms, they had to try to interpret them, and he was analyzing the strategies that they were using to interpret unknown idioms. So he found that the most common strategies were either to try to interpret the idiom based on the context in which it was given, or the second best was based on the literal meaning of the constituents. Maybe it means something about the meaning. So let's look at a different example. Here the narrative is, Isaac yelled across the cliff, face to me. The rush of beating the tempest had his adrenaline pumping. I could see he was scared, yet invigorated. Okay, man, you're up next, he yelled out to me. A sick feeling swept over me. It was indeed my turn to run the gauntlet. There are 2 possible continuations here. They are slightly shortened here. So the first is, I took a deep breath and ran full speed away from the cliff. And the other one is, I took a deep breath and ran full speed towards the edge of the cliff. So our first model is based on the literal meaning of the constituents, and it uses a COMET model trained on ConceptNet. So ConceptNet is a knowledge base containing common sense knowledge about concepts, and COMET is similar to a knowledge-based completion model, and it can retrieve common sense knowledge about words, about the constituents of the idiom. So for example, it tells us that run is used to get exercise. It has the property found on gym, and gauntlet is used as a weapon. We take the top 2 inferences for each of the 6 ConceptNet relations we considered, and then we train a scorer to predict the score for each combination of the narrative, inference, and a candidate continuation. So for example, we would have the narrative followed by some separator token, then the inference, run is used to get exercise, and a separator, and the first candidate continuation. And we would predict the scores for each one of the inferences, and the score for the continuation would be the sum of scores for each of the inferences. And then the model predicts the continuation that has the higher score. And the model is trained end to end, so we don't have direct labels for the inferences, but only for the continuations. Similarly, we also trained a context model. Here we use paracomet. So this is the paragraph level model, paragraph level version of Comet. And it's trained on the atomic knowledge base. So it can reason about causes, effects, and mental states of the participants of an event. For example, it tells us that the narrator sweats from nerves, feels scared, and wants to feel better. So we got a small improvement with the context model and a slightly bigger improvement with the literal model. And we also tried combining them because it seems like they are complementary, but actually the literal model was always preferred. And there's still some room for improvement on the discriminative task. You can see that we still have a few points left to get to human performance. But the more interesting task, I would say, is the generative task. Here, the goal is to, given the narrative containing the idiom, the goal is to generate a plausible continuation. The models are similar in terms of also being based on language models, but now they are trained in a generative setup. So they are provided with the narrative and they need to generate the plausible continuation. We can see that largely the supervised models perform better than the few-shot models, which perform better than the zero-shot models. And this is in terms of BERT scores. So that's the more informative automatic evaluation metric that we had, although it's still not in full correlation to human judgments. Our context and literal models are, again, pretty similar. Now we train them, for this generative setup, we train them with one inference at a time to generate the plausible continuation. So for example, run is used to get exercise, followed by the narrative, input that into the generator, and then the generator needs to predict the plausible continuation. During inference, we predict the logits of each one of the statement with each one of the inferences separately, and then we sum them before we sample the next token. So it's an iterative process. The literal and context model in terms of BERT score performed slightly worse than the baseline GPT model. We also conducted human evaluation by asking crowdsourcing workers to judge 3 endings for a given narrative generated by the supervised baseline, the context model, and the literal model. So the context model was preferred most of the time, and then followed by the baseline and the literal model. And this is in line with what people do based on the experiments by Cooper, because the context strategy was substantially more common and more successful than the second best strategy, which was the literal strategy. Let's look at some example generations. Going back to our Carmen example, these are the references. Dominic is in a relationship with someone else. The goods were available for anyone who wanted them, and Carmen will find someone new to be with. So GPT-2 generated, I'm not up for grabs anymore, so I can focus on something that I'm good at. That's not good because it's confusing the characters. It's Dominic that is not up for grabs anymore, not Carmen, nor the narrator. Bart generated, I know that you will be okay. And that could be fine. Basically, it does contradict what the narrative says, that not thinking that you will be okay, but it may be that the narrator changed her mind based on what Carmen said. So that's fine. T5 generated, he was ready to take his time, which doesn't seem very related. And GPT-2 zero-shot generated, I just need to find a new date. You're coming, right? I asked her, which is so close, but it's incorrect because it's confusing the narrator with Carmen. If it wasn't for the I asked her, it could have been something that Carmen said, and then it would make sense. GPT-3 few-shot nailed it. Carmen will focus on her career and be a lawyer. That's really cool. The context model generated thought Carmen considerate of Dominic's feelings, which is good. And the literal model generated thought about it and decided it was for the best, which is also okay. To recap, we first talked about interpreting implicit meaning. So we talked about models' ability to interpret, for example, baby oil as oil used for babies. And I've shown a model that generalizes existing knowledge about similar noun compounds. It seems that large pre-trained language models to some extent do that too. So that's really good news. But all the models struggle with noun compounds that require common sense knowledge to interpret, such as cheeseburger stabbing. We then talked about recognizing meaning shift. So pre-trained language models are really good at this, but they're not as good at representing non-literal expressions meaningfully. Finally, we talked about interpreting figurative language, specifically focusing on idioms. So idioms are like encrypted language that models need to decrypt. And so I've shown that providing models with better understanding of the context and the properties of the literal senses of the constituent words helps. But this help depends on the quality of the tools that we have for understanding the narrative, the characters, and being able to read between the lines and make common sense inferences. And there's definitely room for improvement there. Thank you.